Physicists are interested in variables that you can quantify, meaning that they go around the universe and look for things you can put a number on. And when you put a number of something, well, it has a unit usually. And there are 7 units that are the most fundamental ones. We call them SI units, standing for Système International, the French for International System. And there are some units in there that you know very well, like the kilogram for mass, the meter for distances, the second for time, and you're used probably to degrees Celsius for temperatures, and here we have kelvins, which is the International System unit. Then the mole is something that's a bit similar to mass but different. It rather has to do with the amount of atoms contained in a substance and not its mass. We have amperes for current, anything that has to do with electricity, and candela for luminosity, but we won't be using it. I've never used it in my career, and we don't care about it for the IB. So there are these 6 SI units that are interesting to us, and let's focus on this Kelvin unit first. Kelvins are interesting because instead of starting at the freezing point of water, like in the degree Celsius system, well, the scale starts at absolute zero, the coldest possible temperature in the universe. 0 Kelvin corresponds to around minus 273 degrees Celsius, where you basically achieve a state of zero energy. So, how cold and how hot can things get in the universe? The temperature in outer space is around 3 Kelvin. So 3 degrees, around 3 degrees above absolute zero. That's very cold. Are we actually here at the coldest temperature ever recorded? Well, no. On Earth, actually, in a lab where scientists were able to achieve a temperature of 170 nanokelvin, meaning 170 billionth of a degree above absolute zero. Now, how hot is our sun? Well, at the surface, it's around 5,800 kelvins, and at the core where helium fusion is happening, it's around 15 million kelvins. There are stars that are at least 10 times more massive than the sun, and we call them red giants. And when these red giants collapse, they form what we call a supernova. It's the most powerful explosion in the universe. And in a supernova, the temperature reaches 100 times 10 to the 9 Kelvin, meaning 100 billion Kelvin. And is that the hottest temperature ever recorded in the universe? Well, the answer is surprisingly no. In a lab on Earth, we were able to achieve a temperature of 4 trillion kelvins, and we managed to achieve this by speeding up gold ions nearly to the speed of light and making them collide together, and obtaining conditions of temperature that, as theory suggests, was the temperature of the universe less than 100th of a second after the Big Bang. Now let's look at sizes as well, because it's quite exciting to see how small things can be in the universe and how large they can be. So let's read this table that I got from Wikipedia. How do we read it? Here we're looking at ranges of orders of magnitudes in meters. So for example, here we're at around from 1 meter to 1,000 meters, things that we can easily represent with our minds because we see them every day, going from a human being to a tall building. Then the millimeter is also quite easy to visualize, okay, like the size of a mosquito. Now it becomes harder when we get to the micrometer, which is dividing a millimeter into 1,000 pieces. Divide this into 1,000 pieces again, and you get the nanometer, and divide this into 10 pieces again, and you get the order of magnitude of the size of an atom, 10 to the minus 10 meters. And maybe you're about to live an amazing paradigm shift if you hear this for the first time, but the size of a nucleus is around 10 to the minus 15 meters, so meaning 10,000 times smaller than the size of the atom. And when we compare the volume of the nucleus to that of the atom, we take the cube of these numbers, we take the ratio of the cubes, resulting in this insane number, the percentage of empty space there is inside an atom. Meaning that if the atom was the size of a football field, well, the nucleus would be a needle in the center of that football field. Let's look at large sizes now, sizes that go beyond our ability of visualization. This one's interesting, 1 light second. What does it mean? Well, When light travels in space, it travels at a speed of 300,000 kilometers per second approximately. So the distance of one light second is the same as 300,000 kilometers, and that's approximately the distance to the moon. How far is the sun? About 8 light minutes. 8 light minutes, meaning that the light of the sun takes about 8 minutes to get to us. So in fact, when you look at the sun, you're always looking at how it was 8 minutes ago. So then, distance to Proxima Centauri, that's interesting as well. That's the star that's the closest to us after the sun, and it's about 4.2 light years away. Now, the size of the Milky Way, the size of our galaxy is about 1 million billion times the size of the Earth. And finally, what's the largest size observed by mankind? Well, it's the size of the observable universe. Actually, we don't know how large the universe is. Maybe it's infinite, but there is at least a portion of it that we can observe, and that's consistent with the Big Bang theory. And it's something that's the size of 10 to the 26 meters. So the image of the needle in the middle of a football field also applies when you compare the size of our galaxy, the Milky Way, to the size of the observable universe. And these telescopes, the light that they get from these edges here, well, remember that when you're looking very far, you're looking at the past, just like when you're looking at the sun, you're looking at the 8-minute-old sun. Well, here we're looking at light that's 13.8 billion years old, and that's the age of the universe. Now, if physics was only about measuring 7 fundamental quantities, well, it wouldn't be that fun, and there's a bunch of other units that are derived from the fundamental SI units. And you'll realize that on this table that I got from Wikipedia again, they say that, for example, newtons and joules are SI units. Well, in fact, in the IB, when we talk about SI units, we really mean SI base units, the 7 that I showed you earlier on. So let's go through this list of units, and I'll tell you a bit about those that are easy to understand, and I'll cross out those that we won't even look at during the IB course. Okay, so let's start with radians. Yes, indeed, we'll measure angles in radians, and pi radians is equal to 180 degrees. You're probably more used to degrees up to now. We won't look at steradians. We will look at hertz. 1 hertz means 1 cycle per second. 1 cycle per second, so this is why the SI equivalent is inverse seconds. And we'll look at hertz in the context of oscillations and waves. For example, in AC current, well, electrons oscillate at a rate of 60 hertz, 60 oscillations per second. Newtons, the units for force. We'll see that force has an equivalence with mass and acceleration when we look at Newton's second law. So this is why the SI equivalent of newtons is kilograms times meters per second squared. Pressure is measured in pascals. A pressure is indeed a force divided by an area, so newtons per meter squared. Joules is a unit we'll use a lot whenever we talk about energy, and watts is closely related to joules because a power is an amount of energy divided by an amount of time. For example, a 1 megawatt windmill produces 1 million joules of energy each second that it functions. The coulomb is the measure of charge. For example, the charge of an electron is equal to minus 1.6 times 10 to the minus 19 coulombs. And the proton has exactly that amount of charge, except that it has a positive sign. The volts, units for potential difference, that one is a bit tricky. We'll get to look at that when studying batteries and electric fields. The farad is the unit for capacitance, which is a way to characterize components in circuits called capacitors, which accumulate charge, and only higher level students will get to look at farads. Then the ohm is the unit for electrical resistance. We'll use it when studying circuits. We won't look at the Siemens. We will use the Weber for higher level students when studying the Faraday's law and how electricity is produced. We'll look at Tesla when studying magnetic fields. It's the strength of a magnetic field. We won't look at inductance. You already know about degrees Celsius. And we won't look at any of these, but we will, except for this one, we will look at radioactivity. For example, a substance that has one atom decaying per second has an activity of 1 becquerel. And that's it. That's basically a summary of all the units that we will use during this IB Physics course. Now that we talked about units and orders of magnitude, we're getting to the last part of this lecture, which is about conversions. And here I'll give you the ultimate method to convert units very efficiently. You may have struggled on this kind of problem before. For example, you were given a quantity in kilometers per hour, 100 kilometers per hour, and asked to convert this into meters per second, which would be SI units. Well, the way to do this is to first rewrite this as 100 times 1 kilometer divided by 1 hour. This is what is implied when you say kilometer per hour. In fact, it's 1 kilometer divided by 1 hour. So now you want to split your work into two tasks, which is first to convert kilometers into meters. That's easy. There's 1,000 meters in 1 kilometer. And in 1 hour, there's 60 minutes, and therefore 60 times 60 seconds, therefore 3,600 seconds. So to convert 100 kilometers per hour into meters per second, you have to do times 1,000 divided by 3,600, which is the same as dividing by 3.6, and you get approximately 28 meters per second. Let's solve the problem the other way around. Converting 100 meters per second into kilometers per hour, it's a bit more tricky because you have to manipulate some fractions. So I have 100 times 1 meter divided by 1 second. I know that 1 meter is 1,000th of a kilometer, and that 1 second is 3,600th of an hour. And therefore, when you work out these fractions here, it's equivalent to multiplying by 3.6. Therefore, 100 meters per second is the same thing as 360 kilometers per hour. And you can use this same method when, for example, you have the problem of converting, for example, 12 meters squared into centimeters squared, let's say. Well, 12 meters squared, that's equal to 12 times 1 meter squared. This is 12 times 100 centimeter squared. And therefore we obtain 12 times 100th squared, which is 10,000. So 12 times 10,000 centimeter squared, meaning in the end 120,000 centimeter squared. Now this method becomes very handy when you're, for example, trying to convert densities. Imagine I have a density of 2 milligrams per centimeter cube, and I want to convert this amount into SI units, so kilograms per meter cube. So how do I do this? I have 2 times 1 milligram on the numerator. Well, 1 milligram is 1,000th of a gram, and therefore a millionth of a kilogram. So I have a millionth of a kilogram up there, and down there I have a centimeter cube. I know that a centimeter is 100th of a meter, and all of this has to be cubed. Therefore, what do I have in the end? I have 2 times. This goes up in the numerator. I get 100 cube on the numerator, and that's 10 to the power of 6. Okay, 10 to the power of 2 to the power of 3. 2 times 3 is 6. And down there I have as well 10 to the power of 6. And I have kilograms up there. I have meter cubes down there. So in fact, in the end, these cancel out, and I'm left with saying that 2 milligrams per centimeter cube is in fact the same thing as 2 kilograms per meter cube. And that's it for today. Thanks for watching.